Hello. Today we are going to discuss about the topic semiconductors. So, what is semiconductor? Okay, a semiconductor is a material that is neither a good conductor nor a good insulator, but that conducts more electricity when heat, light, or voltage applied. Okay, are you clear? So, what are the types of semiconductors? There are 4 types of semiconductor. Based on the energy emission, we can classify the semiconductors into 2 types, that are indirect band gap semiconductors and direct band gap semiconductors. Then next, based on the purity of semiconductors, we can classify the semiconductors as 2 types, that are intrinsic semiconductors and extrinsic semiconductors. We are familiar to this intrinsic and extrinsic semiconductor, isn't it? Yes. Next, what is direct band gap semiconductors? That is, if the crystal momentum of electrons and holes, the crystal momentum means when an electron or hole is moving inside the crystal lattice, a force will be there in acting on that electron, okay, or a hole. So, the force to move an electron or a hole inside the crystal lattice is called crystal momentum, okay. So, if the crystal momentum of electrons, this crystal momentum of both electrons and holes are same in the both conduction band and valence band, if this condition occurs, what will happen? An electron can directly emit a photon. Okay. These type of semiconductors are called direct band gap semiconductors. The example is indium arsenide and gallium arsenide. Okay. So, this valence band means in an atom the outside shell is called valence band. Whenever the outside shell electrons are acquiring some energy, it will excited into conduction band, the next energy level, that is the conduction band. Okay. Okay, the next is indirect band gap semiconductors. In indirect band gap semiconductor, the same thing, the crystal momentum, okay. If the crystal momentum of electrons and holes are not same in both valence band and conduction band, if this force on moving electron is not same as the force on a moving hole, then the crystal momentum is different. So, in this case, we call it as indirect band gap semiconductors. Okay. That example is crystalline silicon and germanium. Then next is based on the purity of semiconductors, we classified semiconductors into 2 types, that are intrinsic semiconductors and extrinsic semiconductor. Okay. The extremely pure form of semiconductor, that means there is no impurity. We haven't added any impurity to the semiconductor crystal. Okay. So, this pure intrinsic semiconductor, the extremely pure form of semiconductor, as there is no impurity, the number of electrons must be equal to number of holes. Okay. At 0 Kelvin temperature, the valence band is completely filled and conduction band is empty. That means the outermost shell electrons are there. Again, the conduction band, we are not giving or supplying any temperature. That is, at 0 Kelvin temperature, the electrons will be in valence band only. They are not excited into conduction band. Okay. When we are increasing the temperature from 0 Kelvin, okay, what will happen? The electrons in the valence band acquire some energy and they jump into the conduction band. How this occurs? The electrons in the valence band are in covalent bonding. So when we are increasing the temperature, what will happen? The covalent bond will break. After a certain temperature, the covalent bond will break and the electron become free electrons, and it moves randomly throughout the crystal. Okay, the free electrons move randomly throughout the crystal, and this moves to the conduction band. Okay, the energy required to break this covalent bond is equal to the band gap energy. Okay, the electrons are in covalent bond, the energy or the temperature we are giving to break this covalent bond is called Eg, or band gap energy. It's 0.72 electron volt for germanium and 1.1 electron volt for silicon semiconductor. Okay, in case of intrinsic semiconductor, the main point noted is, when we are increasing the temperature, the covalent bond will break and the electron become free electrons, and they takes place for the conduction. Okay, so this is intrinsic semiconductor. Then next is extrinsic semiconductor. When we are adding some impure atoms to the pure semiconductor, we will get extrinsic semiconductor. The process of adding this impure atom is called doping. So we are adding the impure atom or a foreign atom into the pure semiconductor crystal in a silicon or in a pure germanium crystal. When we are adding some impurity atoms, okay, such as boron or something, pentavalent or trivalent atoms you are adding, we will be getting extrinsic semiconductor. The two types of extrinsic semiconductors are N-type semiconductor and P-type semiconductor. Okay, let's see what is N-type and P-type. So first one is N-type semiconductor. When a pentavalent impurity means, in a pentavalent impurity, the outer valence shell will having 5 electrons, then it is called pentavalent impurity. Okay, so when a pentavalent impurity, that is phosphorus is atomic number is 15, so 2, 8, 5 will be its configuration. So again 5 electrons is in the valence shell, or antimony, they are the examples of pentavalent impurity, is added. When we are adding a pentavalent impurity into a pure silicon or a pure germanium crystal or a semiconductor, we are adding. So the silicon is having 4 electrons in the valence shell. Look at the picture. Silicon is having 4 valence electrons in the valence shell, outermost orbit. When antimony is a foreign impurity added to this silicon, what will happen? The silicon's 1 electron will get bonded to the 1 electron of the antimony, and again the 4 electrons will engage in the covalent bonding. Again 1 electron will be left there, that electron is free electron from antimony atom. Okay, the remaining 1 electron is not having any silicon atoms valence electron to create a bond, so it will be a free electron. Okay, when a pentavalent impurity is added to the silicon, what will happen? All the 4 electrons will get bonded, covalent bonded. The one remaining electron in the antimony atom is not having any electrons to make or to create a bond, covalent bond. So this 1 electron will be a free electron for conduction. Okay, like this many electrons will be created, that is majority electrons will be created in N-type semiconductor. So here the majority is electrons and the minority is holes. Okay, that is the 5th electron is weakly bound to the parent atom. So for lesser terminal energy, if you are not giving any terminal energy also, the 5th electron is released from the parent atom, that is released from the antimony. So during this process, no hole is created, only the electron is created. Okay. So by this adding the pentavalent impurity, we are getting large number of electrons at room temperature itself. So these electrons are called donor. Again, in p-type semiconductors, when the trivalent impurity is added to the silicon or pure semiconductor atom, that is trivalent means valence shell will contain 3 electrons, trivalent, such as aluminium. When we are taking aluminium, its atomic number is 13, so 283, trivalent impurity, that is valence shell is having 3 electrons. Like that, when we are taking boron's atomic number is 3, so outermost orbit is containing, boron's atomic number is 5, so outermost is containing 2, 3. Okay, so this trivalent impurity is added to the p-type and pure semiconductor. What will happen when the trivalent impurity such as boron is added to the pure semiconductor? The 3 electrons are engaged in covalent bonding. Again, the silicon is having 4 electrons, so these 3 electrons are engaged in covalent bonding, and the aluminium is having only 3 valence electrons, so the silicon is having 4. The silicon's next one electron is not having an electron to create a covalent bond with aluminium, so there a hole is created. Since there is no electron to create a covalent bond, okay, this electron is not having an electron to engage in a covalent bond. So what will happen? A hole is created. Since impure atom accepts 1 electron, okay, if this hole can be filled by accepting anywhere. If electron is there anywhere, it will accept it. So it is called as acceptor level. Okay, holes are majority carriers in this case, and electrons are the minority carriers. Next is some key points. Silicon has smaller leakage current and suitable for high power application. So silicon is mostly preferred over germanium. Okay, also the conductivity of intrinsic semiconductor is small as compared to extrinsic. Also the Fermi level. What is Fermi level? Fermi level is the highest energy state occupied by electrons in a material at absolute zero temperature. That means at absolute zero temperature, the electrons are in valence band. So in this valence band, some electrons will having some energy. Okay, even at zero temperature also, some electrons will having tendency to excite or tendency of having higher energy. So these electrons will in a Fermi level just above other electrons. So this level is called Fermi level. Okay. The next is carrier lifetime. It is the interval of time from breaking the covalent bond until its recombination. While the covalent bond is break and the electron will recombine wherever another electron is like that. So the time required after breaking the covalent bond until its recombination is called carrier lifetime. Then, as we said, what is energy band gap? It is the energy difference between top valence band and bottom conduction band. Okay, how this top valence band, bottom conduction band occurs? After breaking the covalent bond. After breaking the covalent bond, electrons will move from valence band to conduction band. So how much energy is required to break this covalent bond? That is equal to the energy band gap. So this, how much energy is required to break this covalent bond, also equal to the difference between valence band and bottom of the conduction band. Top of the valence band and difference between the top of the valence band and bottom of the conduction band. Okay, that's all about semiconductors lecture. Thank you for watching. Thank you. Thank you.